In this section, we learn about a technique that can be used to find roots of equations, solutions of equations. The method is called Newton's method, and after that Newton, right, the famous guy. And it's an example of an algorithm, a process that can be used to solve equations that may or may not be able, you may or may not be able to solve them analytically through algebra or trigonometric methods. And so, just to kind of give you an idea of one other type, one example of one of these processes is called the bisection method. Now this is not what we're going to be tested on, but just to kind of give you an idea of how a process, an algorithm works if you've never seen them before. So what we do is we're given an equation, and what we first do is rewrite the equation in the form f of x equals 0. Then what we're going to do is we're going to find an interval where f of a and f of b have different signs and the function is continuous. Now, then we know by one of the theorems we saw earlier in the course that if there's different signs and we have a continuous function, it must pass through 0. There must be a root. Alright, so let's take this. So here I've got a graph. Let's take this graph and use and demonstrate what's going on here. So for example, I see that there's a root, and let's say that here's A and here is B. Now, over that interval, f of A is negative and f of B is positive. There must be a root between those. So the next step in the bisection method says calculate the midpoint. Bisect the interval. Alright, so then I bisect the interval, and now here is C. Now, notice that the root is now between A and C. So let me call this maybe C1. Now, I repeat the process. I look at the midpoint of A and C1, and let's say that that midpoint is here. Here's C2. Now the root is between A and C2. Okay, and I repeat the process. I find the midpoint of A and C2, and let me call this point C3. Now the root is between C3 and C2. I repeat. There's C4. Now the root is between C4 and C2. Here's C5. And basically we repeat this process over and over and over again until the interval where the root occurs is sufficiently small. Now, what does sufficiently small mean? Within a certain tolerance, usually. And then we report our latest C value and use that as the solution. So this is the bisection method. It's a fairly slow method, and it isn't used very often. But it is an example of an algorithm that can be used to find roots. So now let's actually look at the method that we're most concerned about in this section, and that's called Newton's method, and we'll build it from scratch. So here's that same graph. And what we're trying to do is we're trying to find this point right here, right? We're trying to find the root of the curve, and here's my function f of x. What Newton's method does, it says, start with a guess. So let me call this mark right here. This is my guess, and it's x0. All right, and what I do is I calculate f of x0. So up here, this is f of x0. And I calculate f prime at x0. And I think of the tangent line. So let me think of this tangent line. I'm going to try and draw. This is not going to work well, probably. So I've drawn the tangent line in blue. It doesn't hit it perfectly, but I hope you understand what's happening there. Now, what Newton's method says is this point right here becomes our new guess. So notice that the tangent line intersects the x-axis. let's call this point x1. Now let's see, can we calculate x1? Well, I know x1 is the x-intercept of the tangent line. Now I know how to find a tangent line. Right? That tangent line is given by y minus the output. F of x0 is equal to the slope f prime at x0 times x minus x0. That's just the point-slope form of the equation of a line through the point x0 f of x0 and with slope f prime of x0. That's the equation of the tangent line. So then this is the same as y equals f prime at x0 times x minus x0 plus f of x0. So now x1, to find x1, x1 is the x-intercept of this line. So let's find the x-intercept. Well, to find an x-intercept, we let y equal 0. So then I'd have 0 equals f prime of x0 by x minus x0 plus f of x0. And now to solve this for x. So let's see, I'd subtract the f of x0, divide by f prime of x0, and add x0. So then x is equal to x0 minus f of x0 over f prime of x0. And this is not x anymore, but now this is x1. And then we repeat the process. Here's x1. Now we take that x1 and we find its function value, f of x1. We find the tangent line. We find where the tangent line intersects, and we call that point x2. And if we go through a similar process, x2 ends up being x1 minus f of x1 over f prime of x1. And then we repeat the process. We take x2, we find its point, f of x2, its y value. We calculate the slope. We find that tangent line. And amazingly enough, x3 is x2 minus f of x2 over f prime of x2. And this is Newton's method. Newton's method says we start with a guess, an x0, and then for the subsequent points, the subsequent x values, we use the form that x sub n, the nth x value, is the n minus 1th x value, subtract the function at x sub n minus 1 over the derivative of the function at x sub n minus 1. This is Newton's method. So then, what do we use as a starting point? Generally, it might be given to us, right? So it could be given. If we have an interval, we can use the midpoint. Or we can just use a guess that's reasonably close to where we think the intercept, the root, is. Now, when will this method fail? Well, there's a few situations where this will fail, and there's extensive information on this. If you go on, Wikipedia or some other site, you can find out information about when it fails. The most obvious place where this could fail would be if we were dividing by 0. So if the derivative was ever 0, then that would cause the method to fail. right? So if we had a stationary point, right? If we had a stationary point, in a sense, what's happening there is, remember, you get a horizontal line. And if we have a horizontal line at that y value, right, if our tangent line is horizontal, it'll never intersect the x-axis. The method fails. Another situation that we could sometimes come across would be what's called the overshoot. And so the overshoot, often what happens with this is we'll end up getting that the x-intercepts, the subsequent x values, keep on oscillating, going from positive to negative and positive to negative, and don't converge. There's a good example of this in the Paul's online notes for this topic. The examples that we're going to see in this course are going to be fairly straightforward and will generally work. If you go into a more in-depth course on what's called numerical analysis, you'll see these specific situations and learn what to do if we get to one of these situations. And in which case we might have to use a different method, or we might have to use a different starting point to find the root. So let's see an example. Here we're going to use Newton's method to find a root accurate to 5 decimal places of x to the 5th equals 6 on 1 to 2. I know that 1 to the 5th is 1, and I know that 2 to the 5th is 32, so somewhere between 1 and 2 seems reasonable, should be a solution. Okay, so the first thing I've got to do is I've got to rewrite this in a sense in a function equals 0. So x to the 5th equals 6. This is equivalent to writing x to the 5th minus 6 is equal to 0. And I want to find a root on 1 to 2. So my function is x to the 5th minus 6. The derivative of the function is 5x to the 4th. Now, what do I use? Well, I know I have a root on 1 to 2. I'm going to say that my x sub 0, my initial guess, I'll use the midpoint. I'll use 1.5. So then my x sub 1, following Newton's method, my x sub 1 is x sub 0, 1.5, minus the function at 1.5 divided by the derivative at 1.5. Now, this isn't necessarily difficult if we have a calculator. We can certainly calculate these things. All right, let's see. Here's my calculator. Let's see, x to the 5th. So let's see, this is, if we put it all in one line, this would be 1.5. And then I'd have to subtract. Let's see, I'm going to have in the numerator, I'm going to have 1.5 to the 5th minus 6. Close that off and divide that by 5 times 1.5 to the 4th power. Get out of the exponent, close that off, and I hit enter. And so x1 is 1.437037037. Now, I can't round too much. If I round this, I'm going to lose accuracy. So again, this is a part of numerical analysis. This calculator has so many what are called floating point, it has so much memory for each number. And so I can't round this. I have to use this number. Right? I have to use this whole number, this answer. So what I'm going to do is I'm going to construct a little algorithm in my calculator to give me this output and then immediately take that output and use it again. So here's what I'm going to do on the TI-84. I'm going to take my initial value, my 1.5, and I'm going to store it as some variable. I'm going to call it A. And I hit enter, and so now 1.5 is stored as A. So now what I'm going to do is I'm going to take the A value, I'm going to subtract A to the 5th, oh, sorry, hit a wrong button there. I'm going to take the A value, I'm going to subtract alpha A to the 5th minus 6 divided by 5A to the 4th. And I'm now going to take that and store it as A. So now if I were to hit enter now, it would do that same process, and it's going to have the 1.437037037 number and store it as A. But I want it to display that number, because if I want to be accurate to 5 decimal places, I need to see what's happening in each step. So on this calculator, if I bring up a colon, which is the alpha button and the decimal, if I hit alpha and decimal, it brings up the colon. And now what I'm going to do is I'm going to hit alpha A, and what it'll do is it'll display that A value. So I hit enter, and I get that same value, 1.43737, or 1.43737. Now here's the neat part. It's now storing this number as A. And so if I do the same process again, if I move up and I bring up that same line, it'll repeat the same process again. So move up, hit enter, that brings up that line that you typed in. Or on older calculators, if you hit second and the enter button, it brings up your last entry. Hit enter again. See, now it used the 1.437 as my X value and went through the process again. So the X1 is approximately 1.437037, and then the X2, which is X1 minus f of X1 over f prime at X1, ended up being 1.431020. And so notice from these last two examples, from X1 and X2, what I see is this root so far has 2 decimal places of accuracy. It didn't change over over that iteration. Second enter. Now the 1.431 is my X value, my A value. Hit enter again. 1.430969. So my X3 is 1.430969. Okay, and notice if I was to round that, now I've got 3 decimal places of accuracy, 1.431. And I repeat the process. 1.430969. Hey, that's the same value, isn't it? So notice, let's look at these last two places, these last two examples. 1.430969085, 1.430969081. In fact, this is now accurate. Notice that this isn't changed up until the, 1, 2, 3, 4. These are accurate to the 8th decimal place. So then, using Newton's method, what I can say is, accurate to 5 decimal places, X is 1.43097, right? Rounding up appropriately, that's the root of the equation to 5 decimal places. Now, do you have to use this calculator method No, you can calculate this each of these terms individually. You're going to have to write down a bunch more numbers. So why not learn how to use an algorithm on your calculator? All right, so here's an example for you to try. Use Newton's method to find a root accurate to 5 decimal places of x squared equals e to the 2 minus x squared on 0 to 2. So now would be a great time to pause. Try this one out on your own. All right, so like before, I will first rewrite this. This is equivalent to writing x squared minus e to the 2 minus x squared is 0. And so then the function is x squared minus e to the 2 minus x squared. And its derivative is then 2x minus e to the 2 minus x squared by negative 2x. So that's what, 2x plus 2x e to the 2 minus x squared. I'll use as my x0, 1, the midpoint. So then my x1, following Newton's method, is x0 minus f of x0 over f prime of x0. So let me go to my calculator. Let me clear out these things. First thing I'm going to do is I'm going to take my initial value, my 1, I'm going to store it as a. And I hit the wrong button there. Take 1 and store it as alpha a. Hit enter. Okay, so now let's set up the code. I need the a value, subtract the function at a. Well, the function at a would be parentheses, alpha a to the second power minus, where's my exponential? Blue and the natural log button. The exponential of 2 minus alpha a to the second power. So the exponential is closed, close the numerator, divide that by parentheses 2 alpha a plus 2 alpha a, and we might need a multiplication here. I'm not sure. Let's try it without. On some calculators you might need a multiplication here. So I'm going to go ahead and put the multiplication in there. Times exponential 2 minus alpha a squared. Close off the denominator. All right, now again, I want to display the a value at each step. So alpha in the decimal brings up the colon, and I want it to display a. And let's hit enter, and it gave me back 1. So that shouldn't have happened, and I realized that I made an error when I input this. I forgot, after I did all that coding, after I typed in that expression with all the a's, I forgot to store the new value as a. So let's hit second enter. And notice right here, I forgot to store the value. I forgot to store the value as a. So let me store as a. And now, alpha colon alpha a. Okay, because now this should be right. This should give me 1/2 if I did this correctly. Okay, close to 1/2. All right, so that fixes the issue. And so now what we do is we repeat the algorithm. So let's see, x1 is 1.231, etc. And so now let's bring up that last line of code again and hit enter. 1.247756. And I think, in fact, if we just hit enter again, it'll do the same process again. Let me just hit enter. There we go. And so it looks to be accurate to 4 decimal places now. Let's hit enter one more time. That should do it. All right, now we have accuracy to 5 decimal places, and so then x is approximately 1.24. So for my solution, x is approximately 1.24786 to 5 decimal places. So that's how we can use Newton's method to find roots of functions. Now, if the function had multiple roots, we would have to start by looking at multiple intervals or multiple starting points to find those multiple roots. But that's how we would use Newton's method. All right, so go practice this a couple times. Make sure you know how to use your calculator. If you have any questions, if you're using a different calculator, please send me a message and I'll be happy to help you with that calculator. All right, have a good one.